Quantum mechanics started a revolution that transformed the modern world. It's hard to imagine life without computers, digital cameras, MRIs, GPS, and smartphones. Yet every one of these modern digital devices is largely just a collection of electronic switches that precisely guide and control the movement of electrons through circuits. The first generation of computers used vacuum tubes as switches to guide electrons through a room-sized maze of circuitry. Each tube has a cathode and a plate. When the cathode is heated, it emits electrons that are attracted to the plate. The grid in the center controls the output. If it's negative, the electron flow decreases. If it's positive, the rate increases as the electrons speed toward the plate. Unfortunately, the tube was not very reliable as a switch. The largest computers needed 18,000 tubes, which used a great deal of power and often failed due to overheating. This posed a significant problem.
The big challenge that needed to be surmounted in finally instigating the technological revolution of the modern electronics age is we needed to make circuits smaller. If you have big circuits, then you can't have small devices. So the challenge was, how do we shrink the size of these electronic circuits and really be able to create microscopic versions of them? Well, if you shrink something down into the microscopic domain, the laws of quantum physics become more and more important.
In the middle of the 20th century, physicists knew they needed to replace the large problematic vacuum tube with a more reliable switch that used less energy. To get there, they tested the electronic conductivity properties of solids, such as crystals and metals, at their atomic level. This launched the field of solid-state physics, a huge leap for industry. In the late 1940s, a team of physicists at Bell Labs made a huge discovery. When two gold point contacts were applied to a crystal of germanium, it produced an output signal greater than its input. They called it a transistor, the fundamental building block of all modern electronics. These tiny transistors function as both a switch and an amplifier. Transistors consumed much less power and controlled electron behavior with more precision than their vacuum tube predecessors.
So you need to have the laws of quantum physics at your disposal to understand how to manipulate the motion of electrons and make them go through these tiny, tiny circuits, these tiny wires. And it was the understanding of the quantum domain that allowed people to fashion microscopic versions of circuits, the integrated circuit, where you've got huge numbers of circuits in tiny little areas.
The conversion from large tubes to tiny transistors began the trend toward miniaturization. Now, individual electronic circuits could be soldered together onto one small plate. This led to the early development of the integrated circuit. By 1971, integrated circuits now had over 2,000 transistors on a single chip of silicon, eliminating the need for wired connections. The first commercially available microprocessors were now in production. Using quantum mechanics, the era of integrated electronics was now underway.
Now, the world is your oyster. You can create microscopic versions of circuits that allow you to have tiny laptop computers and cell phones, allow you to have all sorts of devices which, in the earlier era, the electronics would have taken up a whole room, a whole building. Now all of that happens in a tiny little device.